Dr. Phys, Theoretical Physics, the transfer function. Now we're going to see the powerful technique of using phasors to find the output amplitude relative to the input amplitude for a low-pass filter, and we'll do it rather quickly without even needing calculus. So the way you set this up is using the phasor idea. And we know the answer from our calculation with Green's functions, the convolution, to be given by this formula, and our phase by this formula. And remember, we're driving this system with an input sinusoidal wave, and we're looking at the output, which is a sinusoidal wave with a phase shift given by phi, and the amplitude of the output relative to the input given by this formula. When the frequency that you're sending in is near zero, or let's say less than the cutoff frequency, fairly small compared to the cutoff frequency, then what happens is that you get omega c over omega c, and you get essentially 1. And these low frequencies pass through. When the omega is high compared to the cutoff frequency, then you can neglect the cutoff frequency in the denominator, and you have a big number, and a big number divided into the smaller omega c is essentially 0, and these get filtered out. Well, we do this with the phasor idea. Looking at the input voltage here is going to be equal to the voltage across the resistor plus the voltage across the capacitor. You can think of that as a voltage of input minus the drop here, minus the drop there, getting you back to ground, has to be equal to 0, making that loop. And then by bringing the voltage drops for the resistor and capacitor to the other side, then you have the voltage of input given by the sum of these two voltages. The output is only the voltage across the capacitor. That's what we're tapping off of. So we set this up using the voltage formula here, where you have the input voltage is equal to the voltage across the resistor plus the capacitor. And now we use the generalized Ohm's law for the resistor and the capacitor. Same current is going through both of those, since there's a series arrangement here in that input side. And then for the output, we just tap off the capacitor. Notice that the currents are the same, so that when we do the ratio, we're going to have a cancellation effect. So the input is given by the current times the impedances. Here we sum them. The resistor is simply R, and the capacitor has 1 over j omega c. And doing that, we're ready to take the ratio, and the ratio is the transfer function. The i's cancel, and we have this impedance for the capacitor divided by the total impedance, multiplying top and bottom by j omega c, clears the numerator, and you get 1 plus j omega r times c, which I wrote here as rc. So the magnitude of the transfer function is what we're interested in. And to find that, we're going to first ask you to do a practice problem. That if you find the absolute magnitude of a complex number, remember that's simply the distance you are from the center as a generalization of the absolute magnitude. On the real axis, if you have a plus 5 or a minus 5, you are 5 away from 0. So here we use this similar concept, and that's given by the Pythagorean Theorem, x squared plus y squared is square root. I want you to show me that if you have the absolute value of 1 over something, that it's simply 1 over the absolute value. So I just take the absolute value of what's in the denominator. So you should do that as a practice problem. And then here, by applying that to the denominator, this formula, I get 1 squared plus the omega squared r squared c squared, add together and take the square root. So that is my transmission, the absolute value of the transfer function. And notice that the cutoff frequency is 1 over RC, as we have seen earlier. So by doing that, this is omega squared over omega c squared, and then multiplying top and bottom by omega c. I get omega c up top, and in here, when I bring the omega c inside the square root, it comes in as an omega c squared. And that omega c squared, I'm writing second here, and here the omega c squared cancels the omega c squared in the denominator, and so we have omega c squared, and that's the answer from before. And look at that. A simple phasor setup using the concept of impedance, really. The impedance, the ratio of the impedance across the capacitor over the total impedance is all you have to do. Really didn't need phasors even when you come to think of it, although the phasor language is built in with these impedances as we showed in the previous video. So here we can get the phase by simply multiplying here the top and bottom of this thing with the complex conjugate of the denominator. So I get 1 minus j omega rc up here, and then I get 1 plus the omega rc squared, and then my phase is given by the tangent of the phase angle is given by the tangent. You take the imaginary part minus omega rc and divide by the real part. This is nothing more than doing one of these things here. The tangent of this angle in here, is the imaginary part divided by the real part. So when we do that, we have our phase, which is, guess what we had before. So in summary, we have the transfer function, and that is found very easily by the ratio of those impedances. The one across capacitor plus, for the numerator, then the denominator, it's the capacitor plus the resistor. So you have the sum down here and a capacitor up there. And then the absolute magnitude gives you the transmission for the filter. We got the same results before, and the phase that we figured out by this tangent to get the tangent of the phase, we're all set. We got the same thing as before, and we did not use calculus. And there it is, the input and the output. Nice low pass filter diagram for you. Well, next section we'll talk about Laplace and Fourier transforms and the transfer function.